Yeah, so first of all, of course, thank you for the invitation and then for the possibility to present online. I'm very, very sorry that I cannot be there in person. Hope there will be a next opportunity. I'm sure if there is, I'm sure I'll be very, very happy to visit. All right, so today I'll be talking about, of course, the whole theme of the conference, which is gravitational wave, cosmic sources of gravitational waves, and specifically, after some broad motivation, I'll focus on one of those sources, which I find particularly interesting. And I think you've partially heard about this topic, or at least parts of this topic already, in a talk by Ricardo Ferreira, who presented some days ago, I think he told me. So of course we collaborate. So the part of this work is also a work we've done together with also other collaborators like Chiara Caprini, Oriol Pujolas, Hippolyte Leclerc, Daniel Stier, and then lots of people in Barcelona, Alessio Notari, and other people from past collaborations also in Barcelona like Francesc Ferrer, Edu Massot, and others. All right, so let me start first with some broad motivation. I hope this is not too boring for this audience. So I think my motivation to go into this topic is the investigation of dark sectors. So essentially, one possibility is that new physics, whatever it is, interacts with the standard model only or mostly, of course, via gravitational interactions. And this is, at this point, it has always been observational and a well-motivated possibility, since the evidence we have for this new physics is mostly coming from dark matter and possibly dark energy, which is gravitational evidence. Then those sectors also, in principle, can be abundant or even dominant in the early universe. When by early universe I mean, as it's presented in this slide, I mean the universe before the epoch of recombination, and in particular I even mean before the epoch of BBN, Big Bang nucleosynthesis, which is kind of the last pillars of more or less sure knowledge that we have about the early universe, and afterwards it's kind of an unknown land. We don't even know what energies are reached in this early epoch, possibly as large as 10 to the 16 GeV. So those dark sectors may be abundant in this epoch, and this is why we have the possibility to possibly probe them if we have a way to access this early epoch. Now, one possible way, there are others, of course, in particular there is CMB, large-scale structure, and other, even late universe observations can help us in probing this epoch. However, the one I want to focus on is, of course, a stochastic gravitational wave background, meaning I will consider that new physics may produce sources of gravitational waves that are strong enough such that they generate a stochastic gravitational wave background. In the case, to the best of our understanding, this channel is particularly interesting because it has no competing cosmological standard model background. So, to the best of our understanding, the phase transitions of the standard model do not generate enough gravitational waves that they are observable. But of course, the negative part of it is there are several competing astrophysical backgrounds. I will sketch some of those in the slides. So the type of source I will be focusing on here, again, this is all assuming that there is some new physics that generates this source, are those that are, I call them transient in cosmological history. It means that they're active at a definite epoch in cosmological history, at a definite time scale T star, which is smaller or of the order of the inverse of the Hubble time at a given temperature T star. Oh, what happened? Can you still hear me? Yeah, I don't know what happened. Okay.
Yeah, it's back now.
Yeah, sorry for the glitch. I don't know what happened. Oh, it's happening. Okay. Well, okay. Yeah, sorry about that. So now these are transient in cosmological history, but they're not transient in the sense that they're transient in the detector, right? It's not transient like a binary black hole. So this is really a stochastic background. And in a sketch, basically, you have your Hubble sphere, and then you have a source of a given size inside this Hubble patch. The standard example being that of bubbles of a first-order phase transition, as you can see in this sketch, are typically many bubbles in one Hubble patch. Now, there are also long-lived sources, so these are not really transient in cosmological history. They are also very interesting, and there are, I'm sure, many talks in this conference, and they're very interesting, but I will not talk about them. So a typical gravitational wave spectrum from such a source is peaked at the frequency, which is the inverse time scale of the source at the time. But then there are, of course, high-frequency gravitational waves. In those high-frequency gravitational waves unavoidably probe the microphysical properties of the source. So they are model-dependent. They will depend on exactly what type of new physics or what type of physics in general leads to the source. There are also, on the other hand, super-horizon modes, meaning gravitational wave modes that have wavelengths that are larger than the typical Hubble length. Now, those are instead model independent mostly because they cannot possibly know about the details of the source because of causality. So these are particularly interesting when one wants to select the origin of the source. In particular, in this slide, I'm showing what a typical gravitational wave spectrum from a cosmological source looks like. So you see there is a low frequency tail, which let's call it causality tail because its shape, its functional dependence is set by causality. And it's, as I said, typically model independent, although it is background dependent. It's good to select, this tail is good, I think it's good to select the origin when one observes a cosmological signal. When one observes a gravitational wave signal, it's good to select the origin, whether it's astrophysical or cosmological, in that astrophysical signals may possibly not lead easily to an f-cube slope in the gravitational wave spectrum. There is also, of course, the peak region, and then there is the UV tail, which can be, as I said, is model dependent, and typically in order to be assessed, it requires numerical simulations. Okay, now, as I said, this is typically given by f-cube for a radiation-dominated universe. In fact, with some collaborators, Gabriele Franciolini and Davide Racco, last year we checked that in the frequency range, which is relevant for PTAs, this is actually not exactly an f-cube slope due to deviations from radiation domination caused by the QCD crossover. I can answer more questions about this. I think I don't have more slides here in the main presentation for lack of time. So now if we relate frequencies to temperatures in the early universe, we easily get this relation, which I'm sure you've seen many times probably in this conference already, which is that if you look at temperatures at frequencies around few nanohertz up to 10 nanohertz, then you're really probing temperatures that are around 60 MeV to 100 MeV, so kind of the QCD epoch of the QCD crossover. And if you are instead looking at frequencies relevant for ground-based interferometers, so around 10 hertz, then you're really looking at very, very high energies, possibly around 10 to the 8 GeV. Of course, these estimates, as you see, assume that the time scale of the source here is comparable to a Hubble time at the epoch when the gravitational wave is emitted. Otherwise, as you see, it's linearly depends on this quantity, so you can shift things a bit. In the future, of course, we'll also have LISA, which will be probing a different frequency range, kind of in between this band that I'm showing here. So it will be probing temperatures around 10 to the 2 GeV up to 10 to the 5, 10 to the 6 GeV. All right, so I want to now move to some simple estimates of the amplitude dynamic abundance of these type of sources. And the simple estimate can be obtained by means of the quadrupole formula. Just a quick estimate, just back of the envelope, okay? I'm not pretending to be precise here. Essentially, if you use the quadrupole formula and you plug in here the time scale, you assume that the source is relativistic and you plug in time scale T star, then you will get something like this. You will get that the energy emitted by a certain source, with energy rho source, is given by compared to radiation, is suppressed by this alpha squared, where alpha is the energy fraction of the source. So is how much of the energy density of the radiation background is in the source at the time t star. You see, it's actually alpha star divided 1 plus alpha star and then all squared, but okay, in the limit of small alpha, this is just alpha star squared. And it's also further suppressed by this function here, epsilon, I'm calling it, which is a function of, it's a function of the ratio of the time scale of the source to the Hubble time at the time. And if you do the simple quadruple formula, then you get that the power here is 2. So this factor, this epsilon factor would just be essentially t star over h star to the -1 squared. But for some longer-lived sources, this power law can be 1. Okay, so it's there are these two suppression factors in this formula, and now we can be more concrete in terms of observations and look at what we can actually observe right now. So if we redshift that formula to today, we get the following amplitude in terms of this omega gravitational wave, which is just the energy fraction in gravitational waves today. So we get something of order 10 to the -8 in this quantity when alpha star is more or less of order 0.1, so kind of 10% of the energy density of the universe is in the source, and this epsilon star is of order 1. Okay, so you see here what we are able to probe currently probe. It's this 2 frequency range. This is the O3 LIGO Virgo Kagra sensitivity. And you see here the design sensitivity. So we are precisely around 10 to the -8, 10 to the -9. And with pulsar timing arrays, we are also precisely around 10 to the -8 and 10 to the -9 currently. Now, this plot, of course, is taken from the latest NANO-Grav data release paper. Okay, good. So this, I want to touch briefly further upon PTAs. I'm sure you've heard a lot about this in this conference. So this is a plot we produced by overlapping the evidence regions from the different PTA collaborations. So you see here the European PTA data release 2 in red, in green NANO-Grav 15, and in blue the previous international PTA data release. So what you should read here, these are the parameters that PTA collaborations use to assess the gravitational wave, to describe the gravitational wave background, assuming that it's a simple power law. And below I give you a translation of this parameter, how these parameters translate to omega gravitational waves. So again, you see that what we are seeing, what this collaboration seems to be seeing is again something around 10 to the -8 if you take kind of the central values here for this parameter for the amplitude A, okay? And if you look at the spectral index of this power law, this is given by 5 minus gamma, which is NT. It's shown as NT here in the upper x-axis. You see that there is some evidence for some mildly growing, let's say, spectrum, although also a rather flat spectrum cannot be excluded, of course, at the moment. Okay, I show here also the vanilla astro prediction. I wouldn't give it too much importance since we know that this vanilla astro prediction is probably too vanilla to describe really the astrophysical, the supermassive black hole binary signal. I also wouldn't give too much importance, but I think it's interesting to mention it, to the fact that the competing background from astrophysical, background from supermassive black hole binaries, so far, namely before this latest evidence, had been thought to have a smaller amplitude than the one that is currently observed. So this can be seen here in this paper by in this analysis, in this basically compilation of previous predictions presented in the NANO-Grav paper, where you see that the amplitude of the signal compared to the NANO-Grav observed signal here is consistently lower than what is observed. Of course, as there are always some predictions that kind of match what is observed. And this is from European PTA. So the prediction, astrophysical model prediction is in green, and this is the posteriors that are observed. So again, there might be possibly some surprise here from in terms of the astrophysical background, but the prediction is so uncertain that I wouldn't stress this too much. This instead is the astrophysical backgrounds at LIGO and Virgo and Kagra. So I'm talking, of course, about stochastic backgrounds again. So you can see here the prediction so this is the sensitivity for O3. This is the design sensitivity, and this is a design A+ sensitivity, so it's a kind of updated design. And you see here the prediction based on the current observations of binary neutron stars and binary black holes of what the stochastic background from those sources would look like. So it would kind of lie just below, according to this latest LIGO Virgo Kagra analysis, just below the design sensitivity of LIGO Virgo and Kagra, and possibly within the sensitivity of this A+ design. So these are kind of the competing backgrounds of those frequencies. And now I want to then take this motivation. So based on these observational sensitivities, what can we currently observe in terms of cosmic sources? Using the expression that I derived before, and using the sensitivities that I gave before, then observability now and in the near future essentially requires that the energy fraction of the universe in the source should be of the order 5% or larger, okay, if you want to observe it. In the case in which the source has a timescale compared to Hubble. So the source should really make up a big fraction of the energy density in the early universe. And also, on the other hand, it should also be relatively, its timescale should be quite close to the Hubble timescale. Otherwise, again, the signal would be too suppressive. We wouldn't be able to see it, even if the source would dominate, okay? So that's kind of the two input that we get from observations. Large fraction in the source, large energy fraction in the source. The source should be Hubble-sized, and it should be relativistic, of course. So I see two well-motivated possibilities at this point, given these conclusions. Of course, there might also be other possibilities that I'm not mentioning here. This is, of course, biased also by my personal experience in this field. So two well-motivated possibilities that I like are first-order phase transitions. I'm sure it has been mentioned already. This can lead to gravitational wave via bubble, nucleation, and collisions, or plasma effects, and so on. And another source is some topological defects, in particular domain walls. These are the ones that I will focus on in this talk. And I will show why these are particularly well motivated. But first, let me recall briefly, again, I think you've heard about this with Riccardo's talk, so I will be very fast here. Let me describe quickly what domain walls are. So you have if you have a discrete symmetry, for example, the simplest model that leads to this is that of a real scalar field with a Z2 symmetric potential. Then in the early universe, you may face a spontaneous breaking of this discrete symmetry in the form described by the Kibble mechanism. Essentially, initially you have some thermal potential that keeps the field at the minimum of this thermal potential, but at the maximum of the would-be zero temperature potential. This is as long as the temperature is much larger than the VEV, if you want, of the scalar. Now, once the temperature drops sufficiently enough, then you get the fluctuations will lead to population of these two vacua in a random way, because these are just random fluctuations. So in different regions of the universe, you will populate a different vacua A or vacuum B. And this will lead precisely to the formation of walls that separate these regions with vacuum A from region with vacuum B. There are many concrete implementations of this general and simple idea in beyond the standard model scenarios like compositics, SUSY, possibly metastability, axions, and so on. In fact, I also do have a brief description of how domain walls can also arise in the slightly more complicated model that is that of a complex scalar. So that's the axion, essentially, case. In that case, you first have a U1 symmetry that, again, is spontaneously broken at some high temperature of the order of the VEV of the complex scale of the radial part, okay? At that temperature, you form some defect, which is a cosmic string, which is not particularly relevant for this talk. Later on, at possibly much lower temperature, you can have some non-perturbative effects that preserve a discrete subgroup of this global page-shaping symmetry and lead to a periodic potential like the one I'm showing here. In fact, this picture is exactly what happens to the QCD axion, as you know. That then, in that case, these non-perturbative effects are coming from QCD confinement, okay? So then you preserve a discrete subgroup of the initial symmetry, and once the mass of once the Hubble rate drops to the value of the axion mass, essentially you start oscillating in each region again in different minima, and then you form again domain walls. So these are just two of the simplest examples of scalar field theories in which you form domain walls. Okay. Now here I'm showing you instead how this really looks in their universe. Of course, we cannot see their universe. I don't have observations, unfortunately, to show you, but I do have some snapshots from numerical simulations in expanding background, which we have performed. So this is the best that I can show you. These are 2D slices of gradient energy density of a domain wall network formed by this scalar potential, okay? So typical lambda phi to the 4. And you see here, as time goes on, so these 3 snapshots are supposed to, they show 3 different times in the simulations, and time is growing as you go down in this, in the diagonal, okay? So in the first, you see these lines of bigger energy densities, contours of bigger energy densities are precisely the locations of the walls. And in orange, you see the expanding Hubble box in the simulation. So you see that as the universe expands, the network kind of, it looks like it's simplifying. In fact, what's happening is that the network achieves a scaling regime where there is approximately one Hubble-sized object, one or few Hubble-sized object wall in each Hubble volume, okay? By that property, then one can estimate quickly the energy density in such a network by dimensional analysis. Essentially, there is only one parameter that characterizes the network, that is the mass of the domain wall. The mass, since the domain wall is a 2-dimensional surface, then this is it's a mass which has energy dimension 3. So it's a tension, sigma. And then the other scale in the problem is Hubble, because, as I said, the typical length scale is Hubble, so that's the typical energy density in the network, sigma times h. So that's how these objects behave in the scaling regime, which has been checked. Again, it's achieved typically, unless you do something, you do crazy things, it's typically achieved in domain wall networks, okay, and also in network of different topological defects such as cosmic strings. Now, then I go back to the motivation. How does this property of domain walls relate to the possibility of observing them? So, as I said, the 2 things we need to ensure is that the source makes a large fraction of the energy density at the time when it's active. And this is actually easy to get in both cases, both for a first-order phase transition and for domain walls. Why? For first-order phase transition, in order to get a large fraction, is enough that the dark sector is abundant, which can certainly be in the universe, or yeah, it's basically enough that it's abundant. Or, okay, alternatively, you can consider the transition is very supercooled, so it happens, after some kind of phase of inflation. That can also lead to large fractions, of course. And for domain walls, this is also very easy to ensure, because the scaling regime implies that the fraction of the energy fraction of the source grows with time as a squared. So it grows very rapidly. In fact, this is what's known as the domain wall problem. It grows so rapidly that domain walls dominate eventually the energy density of the universe, okay? So it's easy to get large fraction in both cases. What's more challenging and what distinguishes these 2 setups for the sake of observations is that it's not that easy to get Hubble-sized length scales for a first-order phase transition. The reason is kind of intuitive, is that in order to get something that is Hubble-sized from bubble nucleation, you need a bubble that is of order of the Hubble radius at the time. And this is precisely kind of the limit in which the phase transition can never complete, because the bubbles can never meet and the percolation cannot occur. Of course, this is not to say that this cannot happen. There are scenarios, and I personally have also worked on this, so I do certainly think that there are scenarios that can do it, particularly those with approximately scale invariance. However, I think is challenging. Whereas for domain walls, as I just told you, there is only one scale, one length scale, which is precisely Hubble time, so Hubble scale. So for domain walls, this is much easier to achieve. Okay, this is the reason why from now on I focus on domain walls, and I think that domain walls are interesting from the observational point of view, right, with the current sensitivity. So let's look at constraints also now on the primordial sources, given that we want them to be observable. So we want them to make up a big fraction of the energy density of the universe. Of course, most of it will not go in gravitational waves because the emission, the gravitational channel is always subleading. So where does it go to? Well, we have possibilities. Either it goes to non-relativistic species like dark matter, but since it carries so much energy density, of course it will dominate way before matter radiation equality. We are assuming here that the source is active before BBN. Otherwise, you can play games. So then this possibility is excluded, although a tiny fraction can still end up in some kind of non-relativistic relic. I hope I will have time to go into that later on. So the other possibility is that it goes into some relativistic species, dark radiation essentially, which is, as you know, captured by this parameter delta N effective, that is the energy density compared to the energy density of one neutrino species. And we have bounds coming both from Big Bang nucleosynthesis and especially from CMB, combined with baryon acoustic oscillations measurements, that limit the size of this to be less than 0.3 more or less. So when you translate this into a constraint on alpha, you get that this is of order 0.6, the constraint. But then it means that essentially, you see, you want it to be observable now, but if it has to be observable now, it's most likely, and it's a totally dark sector, most likely it's also observable in the form of dark radiation at CMB surveys or large-scale structure surveys in the near future, in the very near future, okay? Now, of course, there is a totally alternative possibility, namely that the sector is not dark, so not totally dark, meaning that it talks to the standard model. In that case, this energy can be diluted in the standard model because these processes we are considering are happening before Big Bang nucleosynthesis. And then in that case, there is interesting complementary probes, possibly, at colliders and labs. So this is just to motivate that we have ways to, I mean, it's extremely important to have ways to have other signatures of these dark sectors or sectors that talk to a standard model, because probably gravitational waves is not going to be the main or the only way to univocally say that we have found new physics. Okay, so let me show you here what we did back in 2022 before the evidence for the gravitational wave background was found by PTAs. We searched for domain walls because, as you know, there was already strong evidence of a common process, so a common spectrum process, but there was no evidence for Helling-Stauss correlations. So we searched for domain walls in these data sets, IPTA, mostly International PTA Data Release 2, and these are the typical spectra that one uses for domain walls. So as you see, there is a model-independent causality tail, as promised, goes like F cube. And then the high-frequency tail, we used what had been previously assessed by numerical simulations. And now we are, of course, working on this to improve these estimates, which is a UV tail that goes down like 1 over F. Okay. So these are the best fit spectra to the data, to the previous NANO-Grav and IPTA data. And these are the previous, the posteriors that one finds on the parameter of the model. So here we are using a kind of general parameters, not microscopic parameter. We're not using the tension of the domain wall or we are rather using the delta N effective. So if the network decays into dark radiation, then you see that the amount of delta N effective that you would produce to explain the current observations is pretty large. In particular, it mostly lies on the excluded region by Planck 18 plus BAO. And if instead it decays to the standard model, of course, there is no such constraint. And again, as you can see, the energy fraction that it should make is around 10% down to possibly 5%. You see here also that the temperature at which the source should be active, these domain walls, is around 100 MeV down to, let's say, 50 MeV. So it's the epoch of the QCD crossover. This is all as promised from the initial rough estimates. Okay. Now, this analysis has been more recently updated by NANO-Grav 15 with the new data, and you see that more or less it confirms what we found, except that, of course, the signal now is slightly different. In particular, you infer that the temperature is even larger, slightly larger with the new data. So more like above 100 MeV and below 1 GeV. And the energy fraction, again, is around 10%, even a bit, it should even be a bit larger, okay? This is for decay into the standard model on the left, and this is for decay into dark radiation. You can see that when you include the bounds from BBN, which is what this analysis has done following our suggestion, then you, of course, reduce the evidence for cosmological signal very significantly. Okay, now I haven't mentioned actually how to get rid of these objects, but I'm sure Ricardo already did it in his talk. And maybe, of course, many of you are also familiar with this. So, as I said, these domain walls are known to lead to a disaster because their energy density scales so slow that they eventually dominate the energy density of the universe. So this is a virtue if you want to observe them, because they make up they easily make a big fraction of the energy density. But for observational viability, of course, you need to get rid of these objects. So the idea is that one way to do it is to simply take the symmetry, the discrete symmetry, is not exact. Okay, so there is some kind of non-degeneracy between the two minima. I mean, this is kind of a generic prediction because you don't expect these symmetries to be exact necessarily. These are global symmetries. Okay, they're discrete, but they're global symmetries. So you do not. It's probably not so artificial to take a bias between the two minima. And then if there is such a bias, then this bias causes a pressure force on the walls that makes them move essentially. So it causes an acceleration. And once this acceleration beats the Hubble rate, then, so this is this condition here, sigma times h equal to delta V, that is the size of this bias, then you annihilate the network. And the temperature at which this occurs as a function of this parameter delta V and the tension of the domain wall is around GV, 500 MeV, for a bias of the order of 100 MeV, of course, as expected, and a tension of the order of 10 to the 5 GeV cube, so a pretty large tension. Now, the searches so far for these objects have been done assuming that essentially there is an instantaneous annihilation. So essentially, you assume that there is a scaling regime. This network of domain walls has a scaling regime, and then instantaneously annihilate due to the presence of this bias. If you do so, then you find this inferral. We found this inferral in 2022 for the tensions and the energy bias of the network. Again, the fact that it's around the QCD crossover, maybe it's an idea for those of you that are interested in model building. Namely, this bias contribution might be somehow related, if one wants to explain the data with this kind of models, might be somehow related to the QCD scale. And as I mentioned, the tension is pretty large. So yeah, we are talking about beyond LHC scales. Now, this is the confirmation of a proof of what I said, namely that the network annihilates, as we see in numerical simulation in expanding background. So here, on top of that quartic potential, I'm adding a cubic term, and the cubic term precisely tilts the potential in the right way. So you see now, as time advances, you see that the network does not keep the structure that I was showing before of having one structure per Hubble patch, but you can see that there is the formation of closed structure that shrink and collapse. Okay, and there is a lot of radiation. You see here, this is radiation that is coming out of these collapsing walls. Okay, so this annihilation is seen in numerical simulations. You see here this vacuum B, let me call it a false vacuum pocket, because eventually the vacuum that is selected is A, can be typically enclosed in a closed structure that is collapsing. This will become relevant for later part of the talk. Okay, so now the main point of a recent update that we made is that annihilation is not, of course, an instantaneous process. Okay, it takes some time, and this has some interesting implications for gravitational waves. So how does this go? I will show the result of this numerical study that we performed now last year, exactly more or less 1 year ago. So this is how the story goes. So this area fraction is a quantity that kind of can be used as a proxy of whether you are in scaling or not. Okay, basically this is just the area, the comoving area A divided by the comoving volume. So this is a comoving area in domain walls, and you can see here this parameter remains constant more or less when there is no bias. So when the minima are degenerate, you can see eta here is conformal time in our simulations. So you can see initially there is, the network is forming, so it's not in scaling. Eventually, it kind of achieves a scaling regime where this parameter is constant. Okay. Now, in the case where there is a bias instead, these are the dotted and the dot dashed and dashed curves. You see that this parameter at some point deviates from the scaling behavior and drops down, due precisely to the fact that the network is disappearing. So here, the three curves are obtained by varying the size of delta V, okay? And varying the size of delta V corresponds to a different conformal time, which is reported here, at which the annihilation becomes efficient. In this case, we could get only to time 35 due to numerical limitations. So we chose this size of delta V such that the network would annihilate within the time reach of our simulation. So you can see here what happens with the annihilation phase. Within the annihilation phase, there is a false vacuum fraction of, so the fraction of volume in the simulation that is in the false vacuum, so the vacuum that is disappearing, drops pretty rapidly, and this is kind of the main result of our work, or one of the main results, is that we managed to estimate how fast it drops, and it drops exponentially fast. In fact, e to the minus eta cube, where eta annihilation is a parameter again that kind of is, of course, related to the size of the bias, more or less by this factor 1.5, is related to the previous eta delta V. So you can see the network, the network disappears very fast. This is this estimate that we did is crucial in order to understand some of the possible relics of this network, as I will show later. Now here you see how the energy components of the network evolve with time. So you see when you are in scaling regime, these are the solid curves. All the different components, like the kinetic energy of the network, the gradient energy of the network, and the potential energy, all of those achieve a constant value. So you see the gradient is pretty constant. The kinetic energy is pretty constant at late times, although it keeps decreasing a bit here. And this is precisely because the network is achieving this kind of scaling regime. When you include the bias instead, you see the bias grows at some point because it becomes efficient. So more regions are in this are in the region which has a larger energy, and then it just drops down because these regions are shrinking now, right? So you see correspondingly that there is a boost in kinetic energy. So when the bias is active, you see that the energy density is the dotted green curve, increases rather than decreases as in the previous case. And then finally it decreases at late times because at that point the network is really disappearing. So this is crucial. The fact that there is a boost in kinetic energy is crucial for gravitational waves, and as I will show soon. And also the gradients also very rapidly decrease once the network annihilates, of course. Okay, so
Fabrizio, you have 2 minutes left. 2 minutes left.
2 minutes? Yeah. Okay, yeah. So let me conclude on this gravitational wave story. So you can see here what we estimated is that most of the gravitational waves are actually emitted during the annihilation phase. So it's in contrast to what was previously considered, that annihilation is instantaneous and then you just take the signal from scaling and that's it. actually we find, you see that the energy in gravitational wave compared to the total energy in the source keeps increasing, and it saturates only at a much later time, which is approximately twice the time which was previously used essentially to estimate the signal. This means that effectively there is much more gravitational waves emitted by such a network, such an annihilating network. And as you see, this energy in gravitational waves is mostly emitted by the kinetic component because the network is accelerated. So you see here the kinetic component is is dashed. So you see that there is a large contribution coming from the kinetic component. Okay, so in the interest of time, then let me just mention indeed that we find that there is 10 times more, let's say roughly 10 times more gravitational waves than previously thought due to the annihilation phase. And the temperature at which this annihilation occurs is also modified approximately by a factor of 2 compared to the previous estimate. Now, this has an impact on the translation from the macroscopic to the domain wall parameters. So when one goes to omega and T star to the tension and bias parameters. Okay, so I don't know if I have more time to describe the story of black holes a bit.
1 minute.
1 minute. I'll try to be fast here, and I hope you ask questions afterwards. So. The story with black holes is the following. We have described relativistic relics. Now, there can also be non-relativistic relics. As you see, what happens in a typical collapse is that there are closed structures, and in white here is the Hubble patch. So you can have some closed structures that are larger than Hubble patch at some time. These are, of course, very rare. The bigger they are, the more rare they are, but they can exist. Okay, there's a probability that they exist, of course. And they can be very, very large over densities. So once they re-enter the Hubble patch, they can collapse to a black hole if they're over dense enough. So basically, the picture would be that once you annihilate, you generate lots of gravitational waves during the annihilation phase. At the later times, you can have a very rare closed walls that re-enters. The probability of having such walls is very tiny because the fraction of these structures drops exponentially fast, as we estimated. But if they're overdense enough, and if this probability is not too small, then they can be observable. And in particular, what we concluded here is that if you use a conservative threshold for black hole formation, meaning that the Schwarzschild radius of this object is as big as the Hubble sphere when they re-enter the horizon, then you find you overproduce black holes above this solid blue line. So you see overlap with the sensitivity in gravitational waves and temperature. You see that the PTA sensitivity region is still available. And also that if you want to make dark matters from black holes in a totally different temperature region, so totally different tensions and biases, you can also do it, and it can also be observable at future ground-based detectors. Okay, so I think in the lack of, since I don't have time to talk about the future, which is probably good because predicting future is always a risky topic. Okay, thank you.
Thank you.